Hey DevJuniors, forget fixed paths and rigid rules. What if I told you the best way to solve some of the most complex problems in networks is just by being random? Seriously, it sounds a little chaotic. But today, we're re-diving into the brilliant world of Monte Carlo methods in graphs where embracing randomness is your ultimate superpower. This is where probability becomes your best strategy for navigating complexity. It's going to be a fun one, so stick around. So, what exactly is this Monte Carlo method? At its heart, it's not one specific algorithm, but a whole class of them, and they all share one key ingredient: repeated random sampling. Think of it like this. Imagine you have a weirdly shaped six-sided die, and you want to know the probability of rolling a 6. You could try to do some complex physics calculations, or you could just roll it 1,000 or 1,000,000 times and see how often a 6 comes up. That's the essence of Monte Carlo. You're not calculating the exact answer from the start. You're running a bunch of random experiments to estimate it. It's a powerful way to get numerical results for problems that are just too messy to solve directly. It's about using randomness to find an answer that's good enough and often incredibly accurate. Now, how do we apply this idea of random sampling to graphs? We use something called a random walk. Imagine you have a network, like a social media platform or a map of city streets. Pick a starting point, a node in that network. Now, from that node, you look at all the connections leading out of all the edges. Instead of following a pre-planned route, you just randomly pick one of those connections and move to the next node. Then you do it again from your new position, and again and again. You're just wandering through the network with no fixed path, just pure chance at every step. This little digital explorer, this walker, is taking a random stroll through the graph, one random choice at a time. It seems aimless, but this is where the real intelligence of the method starts to show. So, one single random walk is totally unpredictable, right? It could go anywhere. But here's where the magic happens. What if you don't just send out one walker? What if you send out thousands or even millions of them, all starting from random places and wandering around the graph? This is the principle of convergence. At first, it's just a chaotic swarm of activity. But as you let these simulations run, patterns begin to emerge from the noise. You'll notice that some nodes in the graph just naturally get visited more often than others. It's not because they were special from the start, but because the very structure of the network guides the random walks toward them. These frequently visited nodes are often the most important, the most central, or the most influential in the network. The chaos of individual walks converges into a clear, stable pattern. The more walks you run, the more confident you can be in that pattern. It's truly like seeing order emerge from randomness. This leads to a really important concept: probability and estimation. The Monte Carlo method, especially in graphs, rarely gives you a single, exact, mathematically perfect answer. And that's okay. It's not designed for that. Instead, it gives you a very, very good estimation. It's an incredibly powerful tool for problems where finding that exact solution is either computationally impossible or would take an absurdly long time. We're talking years or even centuries of computer time for some really complex networks. Think of it like throwing darts at a target. Your first few throws might be all over the place, but as you throw 1,000 darts, the cluster of hits will get tighter and tighter, and the center of that cluster will be an excellent approximation of the bullseye. The more iterations, the more random walks you run, the better your estimation becomes. It's a trade-off between speed and precision, and it's one that makes solving huge problems actually feasible. So, where do we see this in the real world? Well, one of the most famous examples, in a simplified sense, is Google's original PageRank algorithm. How did Google decide which web pages were the most important and should show up first in search results? They modeled the entire internet as a giant graph, where pages are nodes and links are edges. Then they simulated a user, a random surfer, who just clicks on links randomly. This surfer would jump from page to page, following the links. After running this simulation for a huge number of steps, the pages that were visited most often by this random surfer were considered more important. Why? Because more paths led to them. It's a Monte Carlo idea at its core. Pages with many high-quality links pointing to them would naturally trap the random surfer more often. It was a brilliant way to estimate the authority of a web page by using the power of a random walk. So, let's break it down. What are the pros and cons? On the pro side, Monte Carlo methods are fantastic for very complex, high-dimensional problems where other methods fail. They are also excellent at handling uncertainty and randomness that are already present in a system. They give you a practical way to get an answer when perfection is out of reach. On the con side, they can be computationally expensive. You need to run a lot of iterations to get a reliable result, and that takes processing power. Also, the results are approximations. If you absolutely need a single exact answer, this might not be the right tool for the job. But for a huge range of problems, this trade-off is more than worth it. It's about choosing the right strategy for the problem at hand. Ultimately, the Monte Carlo method teaches us a fascinating lesson. Sometimes, letting go of control and embracing a bit of intelligent randomness is the smartest, most effective way to navigate complexity. It's a beautiful intersection of probability, computer science, and creative problem solving. So now I'm curious, after seeing how this works, where would you use a random walk to solve a problem? Let me know your ideas down in the comments. And if you enjoyed this deep dive, don't forget to like this video and subscribe to DevJunior_ for more explorations into the algorithms that power our world. Thanks for watching.